In this video, we're going to have a look at something called the dot product. So we've had a look at addition and subtraction of vectors and what happens when we multiply by a scalar, so a number. But we want to have a look now at what happens when we multiply one vector by another. Now, when we're talking about vectors, there's two different types of vector multiplication. One is the dot product, which is what we're looking at today, and the other one is called the cross product, and that's not covered in the Extension 1 course. So the dot product tells us the effect that one vector has on another, and it's all to do with how similar in direction they are. So the dot product gets its name from the notation that we use. So if we have one vector u and another vector v, and we want to take the dot product of those, we use a dot to represent that. So that dot is in the middle, not down the bottom like a full stop. So that's why it gets the name dot product. It's also sometimes called the scalar product because when we take the dot product, it will give us a number as our answer, not another vector. So because we get a number, that's what we call a scalar. So it is sometimes called the scalar product, but we don't want to get it confused with scalar multiplication, which is when we were multiplying our vector by a number, say lambda or a scalar. So to avoid that confusion, we're just going to refer to this as the dot product. So there are two different formulas that we can use to calculate the dot product. We're going to have a look at both of them, and which one we use in any given question just depends on the information that we're given or can work out from the question. So let's have a look at the first one. So our first formula says to find the dot product, we're going to take the magnitude of u, so that's the length of this vector, times that by the magnitude of v, so that's the length of this vector, and then times that by cos theta, where theta is the angle between those two vectors. So if we're given the magnitudes, or if we can calculate them from the information that we're given, and if we know that angle in between, then we can calculate the dot product. It also works the other way though. If we're given enough information to find or to know the dot product and to find the magnitudes, then we can work backwards to find the angle between the vectors as well. All right, so let's look at how this formula works, where it comes from. What we're doing is we're looking a little bit at something called projections, which we haven't actually looked at yet. But what we want to do is we want to imagine shining a torch down this way so that it's perpendicular to our vector v. So if we shine that torch down, we're going to end up having a line, that shadow that comes down here from this vector that meets our v at right angles. So what we're doing is we're going to multiply this length here by the length of that vector. So to find this length, if we look at that right angled triangle and do trigonometry, so SOHCAHTOA, then we've got, to find this length, we've got that's our adjacent and our hypotenuse. So we've got cos, so we're going to have the hypotenuse, so our magnitude of u, times cos theta as this length. And they're the two things we're multiplying together, that red length there times the length of the whole vector v. Now it works if we do that the other way as well, if we project the other direction. So instead of our torch being up the top, instead we're going to project so that we're perpendicular to u. So if we do that, we'd end up having to actually extend this one out a little bit, and then we can come across this way. So this is the shadow, this distance here is the shadow that our vector v is casting on u. Now, to find that length, we do the same thing. If we're having a look at the whole red triangle and finding that red length all the way from here to here, that would be the magnitude of v times cos theta. So we'd multiply that by the magnitude of u. So that gives us that formula. So if we have a look at an example, we've got two vectors u and v. We're told that the magnitude of u is 13, the magnitude of v is 10, and the angle between them is 59.5 degrees. So if we want to find the dot product, u dot v, then we're going to do our 13 times 10 times cos of 59.5 degrees. And if you put all of that in your calculator and round off to the nearest whole number, you're going to get about 66. Okay, let's have a look at our second formula. So if we're given two vectors in component form, so u equals ai plus bj, where I and j are our basis unit vectors, and v is ci plus dj, then we can find our dot product by multiplying a by c and then adding b times d. So let's have a look at what that looks like with an example. So we've got our two vectors here and we want to find the dot product u dot v. So to do that, we're going to do our 5 times minus 6. And then we're going to add our 12 times 8. So you can just pop that all in the calculator, but if we do it without, we're going to have minus 30 plus 96. So we would end up with 66 again. So the reason it ends up with the same answer, the same dot product as our last question, is they're actually exactly the same vectors. We've just rounded off that angle is the only difference and why we didn't get exactly 66 last time. So if I were to draw those two vectors on my coordinate plane, so there's my x and y axes, this one's saying I'm going across 5 and up 12. So across 5, up 12 would look something like this. And if I go across negative 6 and up 8, it would look something like this one here. So you can see roughly that it's the same problem as what we had before. If we went through and actually used Pythagoras' theorem, we would have 13 here. And in this one, we would have a 6 and an 8, which would give us our 10. Okay, so let's go back to have a look at that first formula again. But like we said, we can use it to find the size of the angle between two vectors. And that's what this example is asking us to do. So when you've got a question like this, it's always a good idea to draw a rough diagram first, just to get a basic idea of what your answer should be, a ballpark for what our answer should be, so we can check the reasonableness of it. So if u is 3 minus 2, we're going to go across 3 down 2, so it would come down this way somewhere. So that's u. And our v is 1, 7, which would come up this way somewhere. Oh, that didn't work at all. Hang on. Okay, so you can see that it's going to be an obtuse angle from that. And it just gives us, like I said, a ballpark so we can check our answer. So our first formula was this guy here, where we're timesing the magnitudes together and then times cos theta. Okay, so to find our dot product, we can actually use the second formula in here because we have the components. So we can do our 3 times 1 plus our minus 2 times 7. That'll find our dot product using that second formula. And we can find our magnitudes using Pythagoras' theorem. So we're doing 3 squared plus minus 2 squared for the magnitude of u times, and we're going to have 1 squared plus 7 squared for the magnitude of v, and then we're timesing by cos theta, where theta is that angle between our vectors. Now, if we simplify all of that, we'll end up with minus 11 equals the square root of 13 times the square root of 50. We could put those two together, but it doesn't really matter, times cos of theta. Now, rearranging that to get cos theta as the subject, we're going to end up with minus 11 over root 13, root 50. And then if I take cos inverse of this to find my answer, I'll end up with about 116 degrees as my answer. Okay, I just quickly want to run through some of the properties of the dot product. So the first one is the commutative law, which says that if we've got the dot product of two vectors, p and q, it doesn't matter which way round we write those to find the dot product. So pq is the same as q dot p. So that's commutative. If we talk about the length of our vector, if we have the dot product of a vector by itself, that will just end up being the square of the magnitude. The reason that happens, like we said, if we think back to the angle between those two lines, if I have a vector multiplied by itself, so finding the dot product of itself, the angle between those is 0. So when I have cos theta, I would end up with cos of 0, which would just give me 1. So that second part, or the third part, sorry, of the equation disappears, and I would just end up with magnitude of my first vector times the magnitude of my second vector, which is, of course, just itself squared. Okay, the next one is what we call the associative law. So if I've got 3 vectors, p, q, and r, if I take the dot product of q and r, and then I take the dot product of that with p, it doesn't actually matter what order I do that in. So I could do the dot product of p and q first, and then take that with the dot product of r. So that's associative. Distributive also works. So if I had the dot product of p and q plus r, that's the same thing as taking the dot product of p and q plus the dot product of P and R. So we can expand, oh, that's not the dot product. We can expand those brackets like that as well. Okay, last few things are if P dot Q, if we take the dot product and we end up getting 0, the only possible way that that can work is if those two vectors are perpendicular. So it works both ways. If they're perpendicular, the dot product will be 0. And if the dot product is 0, they have to be perpendicular. The reason that works is because if we have perpendicular vectors, the angle between them is 90, and we know that cos of 90 is equal to 0. Okay, and the last one is if P is parallel to Q, then that means that we've either got them going the same direction, so our theta is equal to 0, or if we have them going in the opposite direction, then our theta would be 180 degrees. Now, one of those, if I take cos of 0, I get 1. If I take cos of 180, I get minus 1. So what we end up happening is either we end up with the dot product either being the magnitudes multiplied together, or I should just put a plus or minus, or the negative of the magnitudes added together. So if they're going in the same direction, we just have the magnitudes times together. If they're going in the opposite directions, we would have negative the magnitudes times together. All right, so that's having a look at the dot product.